Alrighty, let's get started. Welcome to Iron Beetle, the show where we took this exciting, awesome database, Tiger Beetle, which is implemented in Zeek and implemented in quite an unusual style with a very strict eye towards performance, towards safety, with deterministic simulation without any kind of dynamic memory allocation at runtime. Okay, I lost my train of thought, but never mind. Let's actually get down to what we were planning to do today, because today is like really a really exciting episode. Okay, and okay, the question is in chat is like, hey, what can we do to distract Nocta today? And as you see, like you don't even have to do like anything to distract me, because I am perfectly capable of distracting myself. So nevertheless, let's try to stay focused, because last time we had a plan and we've went through like 30% of the plan, and today the plan is to finish the remaining 60% of the plan from the last time. So, big picture. We are discussing log structured merge tree, the core of a database. The data structure which stores data on disk, or more specifically, because we actually batch our updates to disk to occur every so many prepares, so that we actually update on disk info only during checkpoint. The actual data structure is comprised from the on disk portion and an in-memory portion. And for the past, I don't know, dozen of episodes, we've been looking at the on disk portion of this data structure, and today and last time we were looking at the in-memory portion. And the way we, well, actually, let me find my terminal. And let me get back to where we were last time. Yeah, last time we started looking at this in-memory path. So to quickly recap, everything is driven from the state machine. And the main thing which actually does execution of transactions is commit function. But, and this is one of the great architectural insights of Tiger Beetle, before we get to commit a whole batch of transfers, we are going to go to disk and load in parallel all the accounts that could be touched by those transfers. So instead of doing the thing where we load a transfer from disk, execute it, load the next transfer, sorry, let me rewind this. And I think that my Twitch stream is broken. Let me try to reconnect then. Hopefully, this will get healed. Okay, so instead of doing the thing where we look at the transfer, look at the two accounts, load two accounts from disk, execute the transfer, get the next transfer, look at the two accounts, load the two accounts from disk, what we actually are going to do is that we can look at all the 8,000 transfers at the same time, load 16,000 of accounts from disk in parallel concurrently, and then proceed to executing the actual 8,000 transfers sequentially, given that all the relevant accounts are actually in cache. And this parallel loading of accounts from disk is driven by prefetch function, which for create transfers does a two-step prefetch. First, we try to load from disk transfers with matching IDs just to check that we don't have duplicate transfers. And then for each of the prefetched transfers, we also go and prefetch the two corresponding accounts. What we've looked at last time is that during prefetch there are two cases. Either we already have this information in cache, in which case prefetch is essentially a do nothing operation because, well, there is nothing to prefetch, or otherwise we fail to find it in any of the in-memory caches and it actually needs to be prefetched from disk, and that's the point where we stopped. We looked at the in-memory path, but we haven't looked at the on-disk path, and that's exactly what are we going to look at today. Okay. Quickly recap. We prefetching certain key. This key could be either in the objects cache, which caches actual transfers and accounts, and if it is there, well, we are done. Otherwise, it might be in the LSM cache. So again, another important reminder, we have grid cache, which caches entire blocks of the grid. So the raw data, the raw bytes as they are stored on disk in the LSM. And we have the object cache, which caches deserialized objects. So if we miss the object cache, there is still a chance that the relevant account is in the LSM cache. And there we try to do our usual LSM lookup where we look hierarchically through all the levels we have, except that we are constrained to only look at the data which is already in memory, which is already in the cache. That's why the result of this lookup is either we don't find anything, or that we found something, in which case we insert the object into the object cache. Or finally, there might be a case that we actually don't know whether this account exists on disk or not. There is simply not enough information in the cache pages, so we need to do disk IO, and this is where we end up in this prefetch keys hash map. So this is the start of the new material, but before that, let me quickly, really quickly, highlight another aspect from the episode, which was 2 episodes ago. So in our domain model, which is in targetable.zig file, each object, like an account, has an ID, which is a user-supplied random number, but it also has a timestamp. Timestamp is an internal ID assigned by our consensus algorithm. And internally, objects are stored by IDs. So when we stored keyed by timestamp. So in the common case, when we want to prefetch something by this U128 ID, we actually first go and figure out what's the relevant timestamp, and then we go and prefetch by timestamp. So this like single logical operation of prefetching by ID requires up to 2 like low-level operations with the underlying LSM tree, because we need to consult both the ID tree and the timestamp tree. And I understand that this might be like very confusing if that's the first episode where you're joined to our middle, but like, sorry, this bit is like where really we need to make use of all information we've been slowly collecting for the past few episodes. Okay, so anyway, if we missed our in-memory lookup, then the data ends up being in the prefetched keys. Prefetched keys is should be just a hash set well, yeah, it is a hash map of what we are prefetching, and where like a hint where in the LSM tree on disk we should be looking for a particular data. Again, because we have this 2-level lookup, we first look up by ID and then we look up by the timestamp. It might be the case that we fail the in-memory cache lookup at either case. So that's why we here can have either an ID or a timestamp. And then this is the level. Again, when we have partial information cached about LSM, what might happen is that we have like level 1 cached, and we looked at the level 1 and the thing isn't there. So we move on to level 2. And we have level 2 cached, and we don't have a thing there. So we moved to level 3. And we don't have level 3 cached. So at this point, we say, okay, the thing is not cached, so we need to look on disk, but we can start from level 3, and this level would be 3. Okay, so let's go back to our state machine prefetch code. So again, we loop synchronously through all the transfers. We, for each transfer, do this prefetching queue. For the case where the thing is in memory, it just does nothing because the thing is prefetched. For the case where it is not in memory, it is like this corresponding key is added to the prefetch, to the prefetch keys. Now we start the actual input-output operation in the prefetch. And you know that this is an input-output operation because this is an asynchronous operation, and it is an asynchronous operation because it receives a callback. Okay, so let's actually start workers. Okay, let's take a look at how it works. And I'm like slightly bemused here because, like, you know, I like had a mental model of like how this operation should work, and this start workers doesn't bode well for that mental model, because I actually don't understand like why, like what could be done here to necessitate start workers. Like, okay, so that's going to be fun for me. I'm going to be trying to figure out this to go with you. Okay, so yeah, I guess important thing is that we have prefetch context. Like, what is prefetch context? Prefetch context should be something owned by the database, right? By the state machine. So prefetch create transfers, prefetch contexts. Okay, yeah, so apparently prefetch contexts is a thing which we store, in state machine for each of the tree, and it stores just a bunch of information which is needed for this asynchronous operation. As a reminder, this is a very general pattern in Tagabitl. There are asynchronous operations, and the way typically asynchronous operations work is that at the end of the day, there is like some kind of like a closure-like structure somewhere on the heap, and all the state which is required to process this asynchronous operation over time is stored in that closure. Now, the two problems, or like, the two opportunities, depending on viewpoint, for Tagabitl is that Tagabitl uses Zeek, and Tagabitl doesn't do dynamic allocations. So first, like, we can't use this pattern because first of all, we don't have a heap. Like we have a heap, but we can't really use it. Like allocating a closure for an IO operation is just not something we are going to do. And the second problem is like we are writing in Zeek, and Zeek doesn't have closures. So like no heap and no closures. How the hell are you going to do asynchronous operations? And the answer is like pretty simple. You just have to manually specify the context for asynchronous operation. You just manually have to enumerate all the data which is required for processing asynchronous operation and store that data somewhere. So for us, the operation is prefetch, and the data which we'll be using during prefetch is this prefetch context. And actually, yes, looking at this, it becomes clear why this thing, doesn't just go and read data, but rather does this start workers thing. Because again, we have prefetch keys, which is like, a bunch of keys we need to prefetch, and we can prefetch them in parallel. So that means rather than doing like one read at a time, we could schedule a bunch of reads. But again, because everything is bounded, for everything in Tagabitl, there is an explicit limit. We cannot just fire infinite amount of input-output operations. So we need to have a well-defined worker pool where each worker, does a single IO operation. And it seems like this is exactly what is happening here. Okay, so let me get back to where we were. I think it was in the groove, and it was called prefetch. Prefetching queue, prefetch. Yeah. Okay, yeah. So we essentially fill the context for this asynchronous operation, which is like the groove, the callback, the snapshot, and again, the snapshot is not something we have like fully completed yet, so just ignore the snapshot for now. And then the iterator of the keys. So this is just stupid iterator over an in-memory hash map. And we do start prefetch. Okay, so we already know that, hey, we are going to prefetch all these keys using this amount of workers. So let's see what is a single worker. Okay, this is, okay, we have something called lookup context because, okay, yeah, right. So kind of like, again, a reminder. These IO contexts, they always stack in Tagabitl. Like, we know that at the end, we are going to hit the grid. So throughout the stack of abstractions, somewhere at the end, we are going to issue grid read and grid writes calls. And we remember that grid reads and grid writes follow exactly the same pattern. To issue a grid read, you need to pass in a context, which is called grid read. So if you open grid, there is like a read and write structs, which are exactly this kind of like context which you pass for every asynchronous operation you need to do. So like this prefetch worker, it has to store this grid context somewhere at the end. And I was like, a little bit like, I expected to see a grid read like right here, but I'm not seeing it. So it actually should be somewhere below, and that means that it should be in this lookup context. And in this lookup context, we have this grid read operation. So okay, and this kind of like, okay, this makes the picture a little bit clearer. So prefetch context stores a bunch of workers, and well, this is like the maximum number of workers we have is the maximum number of read operations we allow. Each worker stores a lookup context, which is, we don't currently know what it is, but it's clear that it is the state which we need to execute lookup operations on the LSM tree, and that lookup context has a single read. And it's important, like, well, we see that lookup context has only a single read, so there isn't going to be any concurrency out there. Okay, so let's get back to start workers. Okay. Okay, as usual, like the usual pattern, we want to do a bunch of operations in parallel. That means that we need to call our callback when all those operations are complete. So we need to know when there is no more outstanding work. And the standard pattern there is to keep a counter and call the callback once the counter reaches 0. So this is exactly what we are doing here, with like a little twist that I think we actually don't know how many of those workers are going to be executing concurrently. So we also add extra +1 to track, like, you know, whether we need to spawn more workers or not. Okay. So we go for each worker, set up its memory, and tell it to start the new iteration. So without looking at this code, I think it's clear that this lookup start next will eventually force a new grid lookup. And apparently, so we pass pointer to us into this worker. So apparently, this thing can also decrement worker spending. Okay, I see worker finished, and who calls that? Okay, yeah. So write this, we might realize that here actually we don't need another worker, and we use that as a signal that, hey, actually we don't need to spawn any more workers, which makes sense. Then what happened to my cursor right now? Okay, so this loop goes and sets up all the workers, and it feels like, well, that's actually interesting. So this code handles the case where all the work happened synchronously. I think that actually should not be possible, because we already did the in-memory lookup upfront, and if there is a chance that all the work could happen synchronously, then we just shouldn't be calling this code at all. But maybe I'm misunderstanding something. I guess there is a case where we just don't need anything to prefetch, but we just, like, you know, call this function to simplify the thing. Anyway, another standard pattern. So basically, at this point, we realize that here actually we are done and there is nothing to do. So we should call the callback. But with asynchronous APIs, the rule is that you either always call the callback synchronously, or you never call the callback synchronously. Because here, sometimes we might call this callback asynchronously if we actually schedule IO. Then even if there is no IO to be done, we still must arrange this callback to be called asynchronously. So we use this on next tick machinery to execute this on the next iteration of the event loop. Because remember, I am not remembering this, but it should be okay. Yeah, remember like that this whole code, like the entirety of TigerBeetle, runs within the context of this event loop. This loop, which, like fetches the next syscall result from IOU ring, then processes it, then asks IOU ring to wait until the next syscall is done. So this on next tick essentially says that, hey, call this callback on the next iteration of this very loop. Okay, so in the callback, we call context finish, and that should just, assert that, hey, actually all work indeed is done. Well, this is also important. This actually goes and clears the list of prefetch keys, and then we go and call a callback. And actually here, like, ideally what we should do here before clearing prefetch key, we should check that context growth object cache contains key for so ideally we should have this verification here, but well, we don't have it, and it's probably not too bad, because if this fails, well, we are going to okay, actually, okay, yeah, actually we could not have this verification because we don't distinguish in our object cache, we don't distinguish objects which are simply not in the cache because they are not cached, and the objects which are not in the cache because they don't exist. So okay, yeah, that's another reason to do like the refactor I was thinking about the last time. Okay, yeah, we spent half an hour to go for the trivial case. Let's then move to the actual IO. So lookup start next. So this thing should enqueue the worker to prefetch next key. Okay, so if we actually don't have anything to prefetch, then we are done. We decrement the context, and that's it. And yeah, okay, yeah, it's okay, yeah. It's kind of like it's a little bit tricky that this finish cannot actually be called from that loop we looked at before, exactly because we had this extra +1. So this we could end up in this finish only if we actually go through the asynchronous path. Okay, otherwise, we could either have an ID or a timestamp. And remember, if we have the ID, what we're going to do is that we're going to do lookup by ID and then lookup by the timestamp. Those two are mostly equivalent. So let's actually ignore the ID path and look only at the timestamp. So okay, if we have a timestamp, we go to our actual LSM tree and request it to look up this value in the tree using timestamp is the key. And at the end of the lookup, we are going to call this callback. We'll look at how this lookup from level storage works internally. But for now, again, we kind of already understand the interfaces here. So this is some asynchronous function, which when completes, we'll call this callback. And the callback Okay. Maybe. Oh, right. Okay. Okay. I was confused. Okay. So, this is the callback. It returns an optional pointer to an object as a result, which makes sense because, well, kind of like if you didn't receive an object, then you get null, and if you received an object, well, you get a pointer to the object. The kind of like usual question is, well, this function does input output. Why we are not considering the possibility that there are input output errors? And the answer, which we covered in one of the previous episodes, is that our grid API is very smartly designed to just dissolve the possibility of an error. So if the grid tries to read something from disk and fails, what it does instead is that it tries to read the same data block from a different replica. So it transparently reads from a disk over the network. And there is like some fancy protocol to do that, but it is invisible from the user of the API. And the guarantee here is that like grid basically just always returns you an object. Like there is no possibility of a failure because there is redundancy and there is always someone who actually has this thing. Okay, so we successfully looked up an object in the tree. We use Zeek's parent pointer pattern to get back to our worker, and we insert the object into our objects cache, which is exactly like the reason why we are doing prefetch. And then we go and loop again. And this again might end up in us calling finish, which might end up in us decrementing work expanded, which might end up in us calling context finish, which might call the callback. Okay, so I guess that's again actually like relatively simple. We just do this lookup in parallel. So let's look at interesting things. Lookup from levels cache. No, not from cache. Actually, why do we even have this lookup from levels cache? It doesn't make sense. Okay, this is something suspicious, but it seems to be unrelated right now, so let's ignore it. Okay, so the meat of the LSM tree, lookup from levels storage, we have. Oh, by the way, I guess we should also take a note how we track the level parameter. So yeah, remember when we failed our lookup from memory, we also figured out the minimal level in the LSM tree which we should start lookup from. So we like carefully thread this information down to the actual input output. So okay, again, we are looking up from this tree. We have a callback because this is a separation, so we must notify the caller when it is done at some point. As any asynchronous separation, we take a context which will store all the data which is required to be kept alive while the operation is in progress. And then what we are trying to look up: the snapshot, which we are ignoring, the key, and the minimal level from which we should start our lookup. Okay, so let's go. First, remember invariant. Capital keeps information about all the tables in memory. So we actually should be able to locate the table this object should be a part of relatively easy. And we go to the manifest, which stores this in-memory information about all the table, and tell the manifest, hey, manifest, please give me an iterator of the tables which might contain this key and which start from this level. Again, why this is an iterator? Because this is an LSM tree. We try to look at the key in level 1, then in level 2, then in level 3, etc., etc., etc. The first level where we found the key is our answer. But if we didn't find a key in a particular level, we should go one level deep. That's why we have an iterator, and it should contain, like, at most LSM levels things. So actually, like, it feels like there's actually missing assert here, because we should, like, we count like how many index block do we have, like how many tables might contain this thing, and we should be able to assert that index block count is less than equal than the number of LSM levels we have minus the level we have started from. It's usual, kind of like there's like one code and rule I target that all our loops should have an upper bound. So actually, ideally we should what we should have done is that, or we should do something like for index block count. Okay, I'm horrible at typing code right now, but we should do something like this. Here we should say const table equal or else const or else break, and here we should just assert that it next equals now. So this is like this loop. This loop is better than this loop because it has a fixed bound on the number of iterations it does. But well, anyway, not going to clean up the code and explain it at the same time because, well, you might actually introduce bugs that way. Anyway, for each table which might contain this key, we sanity check that, well, actually, yes, it could contain this key. And then we say, hey, we are going to fetch this table. And table is its index block, and a block is its address plus its checksum. Again, very, very important. Whenever you read data from disk, you always pass in the checksum because you have a storage fault model. And if you read the data using just the address, you might get a wrong result. So you need to know upfront the checksum for what you're going to read. And the checksum we get from the manifest. We store these checksums in memory. Okay, so index block count equals 0. That means that actually, hey, there aren't any tables which might store this key. So we like finished and we go and we immediately call this callback. And well, like 5 minutes ago, I said that, hey, you should never ever do a thing where you have an API which sometimes calls the callback synchronously and sometimes called asynchronously. Well, this is exactly the example of what you should never ever do. Ideally, this code should be refactored to either schedule this callback through the next tick, or better, to change the call sites for an explicit if and let the call site handle the synchronous case automatically. Okay. Otherwise, well, we should go and start looking up in all these index tables. Yeah, I guess it's useful to take a look at what we store in the lookup context, and it seems relatively straightforward. We store the index tables, which we should be looking at, and we know the upper bound for the number of input tables. Then we store. Okay. Yeah. Okay. This is kind of like, this might store at most LSM level tables of tables, but actually not all of them might be initialized. So we actually, store index block count here. So like, maybe like, okay, so this is like, actually this is like SD bounded array, but like oftentimes we just like open code this construct because it is easy enough and like, syntactically it's easier. Okay, then the index block which we are currently reading, which is 0. And then kind of like, okay, remember that our tables are like one level deep. There is like index block, and then there's a bunch of data blocks which are directly referred by the index block. So when we are looking up the value in the index table, we first read the index block, and then we read a single data block. So the like state in our synchronous operation is which table we are currently dealing with, and we either have data block for this table or we are yet to get to it because we need to read the index block. Okay, and finally, like the callback, what we, as usual, what we call at the end of our lookup. Okay, excellent question in the chat. Can I explain again why we are not allowed to mix sync and async callbacks? Well, I cannot explain it again because I don't think I've actually explained this. I just like, just like gave this as like one of like the 10 commandments of that on that stone table, that like thou shalt not mix async and synchronous callbacks. But yes, there is actually a rationale for why you don't need, why you can't do this. And there is actually two specific cases why this is a bad idea. One is that this can lead to a stack overflow. So let's. Okay, actually, yeah, I'm wondering if we could actually get the stack overflow here. So okay, let me get back to the groove and lookup start next. So okay, so imagine we are calling lookup start next, and this lookup start next ends up calling this lookup from level storage pass lookup object callback. And now imagine that this callback is invoked synchronously. So we go here, and here we like, go and call this lookup start next. So we are back in this loop, and we go here again, and we could this again, but again, this is all on a single stack. So there is like lookup start next, lookup start next, lookup start next, and eventually this overflows the stack, and this is like very bad. So this is like, very easy, like direct and this might actually happen here. Like this is exactly what we do. Okay, so this is okay. This is bad. So this is not just, hey, like we need to like maybe it does better. Like okay, this we need to fix it, because like this exactly can happen in this code, because okay, in lookup from level storage there is a code path where we invoke the callback synchronously, and this callback is this lookup object callback, and it's will go here. And given that at the worst case we are going to have like 16,000 of these lookups one after another, this might crash it. Well, maybe at runtime this actually wouldn't be happening because, as I've said again, this case where we can complete immediately should be impossible because, well, when we prefetch, when we enqueue something for a prefetch, we know that it is not in memory. But still, this is at least very suspicious. Okay, but there is a much kind of like, from my point of view, stronger but also much more philosophical reason why you should never ever do this. And this has to do with invariance. So imagine that you have like some object, like, I don't know, well, like prefetch worker, perfectly fine object. So it has some method, like do something. Worker. Now, this object probably has some invariance. And like, you know, as usual, like, you know, you like, especially if this is a public method, what you want to do is that at the start of the method, you like check that fulfills that like these invariants are actually correct. And then at the end of this method, you also want to check that invariants are actually correct. But like, you know, within this method, inside this implementation, you actually might as well violate the invariants, because that's kind of like the thing. Like, everything is like transactional. You cannot like always keep invariants true all the time. Like, I don't know, there is an invariant with like debits equals credits, but when you do like +1 to debits and +1 to credits, there is a point in code where you like incremented one but don't increment it in the other. So this invariant only stays like between changes to the system, and while you are changing the system, while you are changing the object, the invariants might be violated. So now imagine that, like, you know, we have like code like break invariant. And here we have a code like restore invariant. And here we call async function. And we have this callback here. So the problem is that if this call async function isn't actually async, and it ends up calling the callback right here, the callback will observe broken invariants. And this is like a very bad. This is a source of many vulnerabilities, many bugs. This is like, you know, this like reentrancy problem. This actually kind of like the critical soundness bug for like one cell crate in Rust. Like, there's like this exact like invariant where, like, you know, you like you are in the middle of modifying an object, and then callback fires and re-enters your object and observes broken invariants, and then everything is broken. So hopefully this like actually answers this question, why callbacks should either always be synchronous or always be asynchronous. Okay, so thank you, Brian. Mission accomplished. You successfully distracted me. So now I need to recall where we were. Okay, so we were in a lookup from levels storage, and there we were, oh yeah, right. And there we were looking at what we store in our lookup context. And again, that's like pretty simple. We need to do a lookup from a bunch of tables, and lookup in a table is a two-step process. First, we look up the index block, then we look up the data block. So that's our state. All the index block we need to look up in the current index block we are looking into, and optional data block, depending on where we are at the stage where we are reading the index block or where we are reading the corresponding data block. Okay, so read index block, super simple. We just go to the grid, and read the block with the address we know and with the checksum we know. And as usual, pass the callback. In the callback, well, we get our block. We know that this block stores the table. So we kind of like decode / deserialize this table, but in fact, like we actually just cast row bytes. And again, this is like a very like subtle but key observation. Normally, when you do some IO, you cannot just like cast bytes, because, well, even if you know that, hey, 5 minutes ago you wrote this data at this place on disk, when you read it back, it might actually get corrupted. So you always should do some sanity check. But for us, because we have already verified our cryptographic checksum, we know that the data is actually safe to cast. So okay, yeah, I guess you could you could do something that like that in Rust, like it will boil down to something like, hey, this unsafe block is correct only if and only if p equals and p is false or something like that. Because, well, the actual fact that you are relying here is that if you get a matching cryptographic hash, then it must be exactly the same data, because get on collision otherwise is computationally infeasible. Okay, so we okay, where is this index block for keys? This okay, I'm lost and my back button doesn't work, sorry. Dear, where we were. It was lookup from level storage. Okay. Blocks for key. Also, kind of like coming back to the tip, like how do you like navigate large code bases? Well, like grabbing across the code base is like hilariously effective. And again, like there is a neat LSP feature which allows you to look up all the symbols in the code base. It is not implemented in the ZLS, and I actually wanted like for ages, like basically like on my second day at Hagabital, I opened a ZLS issue which said, hey, we should do this because it's like really important, and I actually volunteered to do this, but I ended up not doing this because, well, it's just so easy to grab for symbols in Zeek that you don't actually need it. So okay, this is it, and this is super simple. So we have our index block. As a reminder, index block stores pointers to data block. So it stores for each data block in this table, it stores this data block checksum, this data block address, and like the minimum key in this data block. So to locate the data block, we binary search for a given key. We get the index in our we get, okay, yeah, right. So we binary search for key, and what we get back here is okay, no, I'm still confused. Index block index. Well, of course, if you type without typos, it is much easier to use this grab the whole code base thing. Okay, right. So index data block for keys does a binary search in the array of keys and returns an index. Then we use that index to look up the corresponding address and checksum in the array of addresses and the checksums. And we get this address and checksum. and we set it to our state. So now we are reading this data block and this checksum, and we go and read this data block. And then again, a synchronous operation. And again, this actually might go to a different replica and read this data block from someone else's disk, which is like, I mean, this is like fascinating. And every time I like read a code which does this, I am like, wow, this is like super smart. Okay, anyway, we get this block, no matter like where we get it, because again, when we read this block, we know it's checksum. Then we go and we binary search inside this data block, and if we found, then we call the callback with the found value, which might be tombstone. As a reminder, to delete data from the LSM tree, due to this hierarchical lookup structure, what you do is that you add a tombstone to the first level. Okay, so if we haven't found our value in the current level, well, we need to advance to the next level, and this is exactly what this code does. We advance to the next level. So we say, okay, we are now going to read the next index block. But if it turns out that actually we already read all the index blocks and we haven't found the key yet, well, then we are done and we call our original callback. If that's not the key, okay, we reset our data block to null, and then we go and read the next index block. And now it's going to be the next index block because we have incremented our index block counter here, and okay, yeah, right, we have this assert here. Okay, I think we are basically done here, and now I only need to remember which is this here we are talking about. Okay, let's try to unwind all the way up to the groove. So we were looking at the prefetch, which called prefetch setup workers, which started a lookup, and the worker, it picks the next key it needs to look up, and then, wow, actually, okay, this is buggy. Well, not buggy, but we really should be sorting the keys before we do lookup. So it seems like you know, okay, what we do here, prefetch. Okay, yeah, yeah. It seems like here, like we should do something like prefetch key sort, or like, you know, some such, because if we actually, well, prefetch key in a sorted order, that means that we are going to likely look up at the exact same objects in our tree rather than like doing random access across all the different levels. So yeah, this is potentially something which is worth doing. Anyway, so yeah, we like our core loop is that you have like a bunch of worker which process concurrently. Each worker fetches the key and then like does the lookup in the storage, which is that, hey, let's read a bunch of index tables code, which eventually calls a lookup object, which eventually calls this callback, where we add the object in the cache and then proceed the next object until we are finished, until we figure out that, hey, actually all the workers are done, and then we finish the entire thing. We call the callback, which ends up calling this callback, which is this callback, which says, and again, we might actually prefetch like a bunch of like different things, but kind of like, yeah, in the end, after we prefetched all the data, we are going to call this callback, which in turn will go all the way up to the replica. And this, okay, this is like one part of like the navigation where like sadly like there isn't like, you know, some static thing you could just look for, like we should just know, like, you know, you see, okay, so we are like calling prefetch, and then we call the callback. Like, what is the callback? What you are doing after the prefetch? And well, here you just have to grab for this state machine prefetch. So this is replica. Replica, when it decides that it needs to commit something, it runs prefetch on the state machine, and then it's actually going to be like a bunch of other stuff, because, well, things might get canceled, which we'll cover at some point, and then we might do like checkpoint or not. But at some point, okay, at some point, where does this happen? Well, okay, I'm lost here. Okay, but at some point, we are after we have prefetch things, we actually go and say, okay, now go and commit this data given what we have prefetched. And as we can observe here, by the absence of a callback, and as we can observe here, again, by the absence of a callback, commit is actually a synchronous operation. And again, this is like one of the biggest architectural insights of Trigabital. We separate synchronous commit, synchronous in order sequential commit, from asynchronous parallel concurrent IOIN prefetch. Yeah, because commit is also pure. And how exactly commit proceeds is going to be the topic of our next episode at 5 p.m. UTC next Thursday, where we hopefully finally will finish proceeding with the plan we had a week ago for the last week episode. So again, I kind of like teased that today we'll finish the 60% of what we started yesterday. Sadly, we finished only 30%. So 30% is still left for the next time. Thank you for joining today. Thank you for trying to distract me with questions, and see you next week. And if for some reason you are not watching this right now live on Twitch, and if you missed this video, well, the video is always on YouTube, on Trigabital YouTube channel, so you could watch it there. Although I'm not sure why I'm telling you this if you're not watching it anyway. Okay, thanks folks, and goodbye.